With the advent of autonomous vehicles and the overall shift towards the use of renewable energy to power our vehicles, the scenario of having a fleet of autonomous electric vehicles that replace regular cabs or taxis or even transportation services is not that far into the future. Manually charging such fleets would become a task in itself. What we have designed is a robotic charging mechanism, a SCARA Type tooling robot that offers 5 degrees of freedom for the end effector. It is capable of detecting the charging port of the parked vehicle, triangulate its position to autonomously safely plug in, complete the charging cycle, and then plug out for the next car to come in. To simplify the problem at hand, we fix a bounding box for the charging port in which the vehicle is guaranteed to park given its autonomous nature. This gives us a fixed field of view that we would need to check for detecting and triangulating the charging port. The manipulator is first taken from a random initial position to one that has a complete view of the bounding box. We have assumed a camera to be mounted on the end effector that takes in the field of view and uses computer vision to correctly determine the pose of the charging port, its coordinates in x, y, and z, plus the orientation of its surface. To implement our mechanism, we used a combination of MATLAB, Simulink, and Simscape Multibody. The manipulator was designed on SolidWorks, and the CAD files were then imported into Multibody for the simulation. MATLAB was used for the initial inverse kinematics calculations that would be required to plan a path in the joint space, from the initial position to its final destination, just in front of the charging port before plugging in. As can be seen, in MATLAB we have taken various constraints for the robotic manipulator that we designed. We have the calculated link lengths for our manipulator, and we have set up symbolic expressions for the inverse kinematic equations that you will need to solve. Theta 1 and theta 2 are then calculated. The final positions of these values are calculated so that the end effector reaches right in front of the port that you would need to plug into. Since our inverse kinematic equations would give us two solutions for theta 1 and theta 2 once calculated, we need to choose the correct set of final thetas for our links 1 and 2 such that we find the most efficient approach towards the charging port. This could be either from the left or from the right. The following code compares both the approaches and takes the most time efficient one into consideration. Moving below, since the camera is mounted on top of the end effector and does not symbolify the center of the end effector itself that needs to plug in, whatever the camera sees needs to be offset by some amount. The XYZ coordinates seen by the camera now need to be transformed into what the end effector is supposed to see for accurate plugging in. These can be seen over here, as this function calculates whatever the offsets are required. Simulink along with Simscape Multibody is now used to take into consideration the constraints given by MATLAB and the final calculated values for theta 1 and theta 2 and move our CAD model to simulate it. As can be seen, our Simulink environment contains two subsystems. The trajectory planning subsystem gives outputs for theta 1, 2, 3, 4 and the z-axis motion. Inside the subsystem, we can see a simple linear interpolation from our initial thetas to our final thetas, which are outputted later on. We also see interpolation in the z-axis for the up-down motion of the manipulator to align correctly with the port. One thing to notice is that during trajectory planning, our initial motion is to move the end effector just towards the charging port and stop right in front of it. For the plugging in motion, we use a task space trajectory to plug in smoothly straight into the port. For this, we've set up a Simulink subsystem like this. We have the required x and y interpolations, and this gets inputted into an inverse kinematic block that we have set up over here that translates x and y coordinates to the required theta 1, theta 2 instantaneously. Our x and y interpolations are fed through the subsystem, and we get an interpolation for theta 1 and theta 2, thus giving us joint space values for what the model needs to traverse. Once the Simulink model is run, our manipulator is able to traverse a complete path from its initial position to the end effector, plugging in and plugging out. This is demonstrated here. As can be seen, our manipulator is now moving from a random initial position to its initial position, where it will have a complete field of view of the required bounding box. It stops right here for maximum field of view and detects where the port is supposed to be. Once the coordinates are triangulated, it starts its approach towards the port. Links 1 and link 2 move towards the end effector, and we also adjust our height of the end effector in z-axis. The two links rotate in joint space, since the trajectory is planned that way. Our port moves nearer to the end effector, and the end effector then aligns itself with the orientation of the port. It stops right in front of the port. Now we have a task space trajectory that is planned and then traversed to plug in smoothly right into the port. This is done by instantaneously calculating the required theta1 and theta2 for both the links so that the port is able to plug in smoothly. Once the charging cycle is completed, our port then detaches from our end effector then detaches from the port, traversing the path it had taken to plug in, and then returns back to its initial position. The camera is mounted on top of this platform over here. That is why we require an offset when calculating.